show that the relation R1 on R, so here R is the set of all real numbers, which is defined as the ordered pair A comma B belonging to the relation R1 if and only if we have 1 plus AB greater than 0 for all values of A and B belonging to the real number set. We have to show that it is reflexive and symmetric but not transitive. Okay, let us begin. So here, let's try to understand the problem first. Here we have a relation R1. So R1 is defined on the set of real number, meaning R1 has to be a subset of the Cartesian product of R with itself. Fine. And then what is R1 here? So R1 is defined as the set of ordered pairs A comma B, such that we have A comma B both belonging to the set of real numbers, and the relationship between A and B is such that 1 plus the product of A and B, this must be greater than 0. So this is our relation R1. Now we have to show that the relation R1 is reflexive and symmetric but not transitive. Okay, let's begin with the first part. Let's see whether it is reflexive or not. Okay, of course it's going to be reflexive, but we'll have to verify that it is indeed a reflexive relation. So for this, what we'll do, we're going to suppose an element, an arbitrary element A. So let A be an arbitrary element. In essence, what we are saying that A belongs to the set of real numbers R. Now, we know that 1 plus A squared, this is always going to be 0 because A is a real number, so it could be positive or negative. But when we square it, it's going to be a positive number. And then when we add 1 to it, it's definitely going to be greater than 0. So if 1 plus A squared is greater than 0, this means that we can rewrite this expression as 1 plus A multiplied to A greater than 0. Fine. So what does it mean? This simply tells us that we have the ordered pair A comma A belonging to the relation R1. Now that's the definition of R1. R1 is the set of ordered pairs A comma B. If we replace B with A, then what we get is 1 plus A square greater than 0. So here we know for a fact that 1 plus A square is indeed greater than 0, and we are able to show that the ordered pair A comma A belongs to R1. Now this is the condition for reflexivity. So this means that we can say thus the relation R1 is indeed reflexive. So it is a reflexive relation on the set of real numbers R, the Cartesian product of R with R. Okay, so R1 is a reflexive relation. Now let's go to the second one where we'll show that R1 is symmetric. So we'll check for its symmetry. Now to check for the symmetry, what we'll have to do here, we'll have to consider two elements. So let's say let A and B be two arbitrary elements that belongs to the set of real numbers. Fine. Now we will consider that A comma B, we'll suppose that A comma B belongs to the relation R1. So we are supposing it. Now what does it tell us? If A comma B belongs to R1, this means that 1 plus A times B must be greater than 0. That is what the relation R1 stands for. Now we can rewrite the expression 1 plus AB greater than 0 as 1 plus B times A greater than 0. Now 1 plus B times A greater than 0 is only telling us that the ordered pair B comma A must belong to R1 as well. So that means we started out by considering that A comma B belongs to R1, and we were able to show that the ordered pair B comma A also belongs to R1, and this is the condition for symmetry. So here what we have shown that thus the relation R1 is symmetric. This is a symmetric relation. Fine. So we were able to show that R1 is both transitive and symmetric. Now we will go for transitivity. Now next we need to show that the given relation R1 is not transitive. But let's first try to understand what this being transitive means. So let's say we have an ordered pair A comma B belonging to the relation R1, and we have another ordered pair B comma C belonging to R1 as well. Then this must imply that the ordered pair A comma C must also belong to R1. Then we can say that the given relation R1 is transitive. However, for our case, we'll have to show that A comma C does not belong to R1. So here what we'll do, we're going to take very specific examples. So let's say if we consider A to be equals to -8, let's say B equals to -2, and C equals to 1/4. Okay, so here we are saying that -8 comma -2 that belongs to R1. We can verify that because this simply means that we have 1 plus AB. So here A is -8 and B is -2. So this gives us what? We have -8 times -2. So that gives us 16. So 16 added to 1, that's 17. And definitely 17 is going to be greater than 0. Okay. So this is true that -8 comma -2 indeed belongs to R1. Next, if we take -2 comma 1/4. So that means here we are considering the ordered pair B comma C. So this is also going to belong to R1. So here we can check that. So we have 1 added to -2 multiplied to 1/4. So this is going to give us, so we have 1 minus 1/2. So that's going to give us positive 1/2, and that's also greater than 0. So here we have shown that the second ordered pair B comma C also belongs to R1. However, but we see that if we take the ordered pair, so A comma C, that means we are going to take -8 comma positive 1/4. This is, what is this? This simply means that we have 1 plus -8 multiplied to 1/4. So this is going to give us -1, and -1 is not greater than 0. So this is not this ordered pair -8 comma positive 1/4. This does not belong to the relation R1. So this means that thus we can say that R1, the relation R1 is not transitive. So not transitive. So here we have successfully showed that the relation R1 is reflexive and it is symmetric, but it is not transitive. And immediately we can also say that the relation is not going to be an equivalence relation.